Hi, let's just start this section B in the project P1 on designing circuits from the initial truth table that is going to be given as the specification, okay? So now the starting point in the design process is the truth table because it says exactly what the circuit has to do for every single combination. We can have it in this table format, or instead we can have it whatever way, as a product of maxterms or as well as a sum of minterms, because whatever equation is the same as the truth table. There is no doubt about this. One of the equations is all the terms that are considered to be zero, and the other equation, the sum of minterms, means that we are going to count all the terms that are given a 1 in the truth table. So in whatever way, we have the truth table as the specification of the circuit. And then, because this is a design problem, here we are plenty of possibilities, because it's all about creativity and invention, you know. The idea is that every one of you can have very easy a different circuit. Sometimes you will find circuits which are more complex than others, and well, investigation perhaps which one is the best is another problem. Now we are not now at this level. We are simply trying to invent as many circuits as possible, or at least let's see the variety of circuits that here just at the beginning of the P1 project we can invent. Okay, essentially there is something very simple here if we have to invent a circuit, because we can use the canonical equations. If we have in mind the product of maxterms or the sum of minterms, we have already circuits, because the equations are directly a circuit. If you represent it as a logic diagram, is a circuit already. So that way is easy and has nothing to say, nothing else to say. You've got the circuit because the circuit represents directly the sum of maxterms, the minterms, or the product of maxterms. Whatever way, you have at least two different circuits now, and perhaps this is the way to start. Okay, but basically that is not always possible to do, because imagine a truth table that has 250 different maxterms. That is going to be an incredibly large circuit that cannot be solved in this simple way, just taking the maxterm products. So you have to do something else. So normally what we are going to do is to go through a process that is called minimization. And this is by means, in this case, instead of the Carnot map, we will choose a program, an application, Minilog, which is based on an espresso algorithm. And using this application, we will get as a result an equation as well as we have at the beginning, this time an equation, but which is going to be minimized. I mean, it's going to be a lot more simple than the original one, which is the product of maxterms or the sum of minterms. So from using this application, we'll be able to invent, okay, two different equations, the sum of products or the products of sums, whatever way, right? And this means that if we have two more equations, we have indeed two more circuits, the circuit 3 and the circuit 4, naturally. So those 4 circuits are almost immediate. 2 of them requires nothing but drawing the equation, and the other 2 are obtained using this application. So that's a way to get 4 different circuits, because apart from that, you can imagine that later you can mix any kind of equation. That is always possible. There is no need to have a perfect sum of products or a perfect product of sums or sum of whatever. You know, you can mix them all, and essentially you can get any circuit, like the circuit C that was given to you at the very beginning to analyze. That was a circuit which was a little bit of everything. SHOR gates, NAND gates, AND gates, so it was something like that. What you get when you go mixing equations, but is well, from this point of view, what you get is another realization, another implementation of the truth table. So this is not a problem. You have the circuit now 9 if you go like this way. So finally, if there is another possibility here, after those initial ones that we have commented, there is the other possibility that implies that if you already have a circuit, for example, from a product or sum of products, you can go and modify it a little bit more. For example, you may like to introduce another constraint, which means using, for example, in this structure only NAND. And this can be solved applying some Boole's algebra here, another trick, so that you can get even another circuit, the circuit 5, for example, which consists of only NAND gates like this one here, right? A NAND of 4 inputs, for example. This is very possible here. So to get a final circuit which is composed of only NAND. You can do that in the dual way, consisting, you can invent a circuit that has only NAND, or the other way, only NOR. That depends in one way or another. Every way is possible. And there is even another step that you can go a little bit farther away. If you have a circuit like this, which is consisting of only NAND, for example, the one that you derived from the circuit that was canonical based on maxterms. So if you have such a circuit 1, you can have a circuit 7 which is only NAND, very well. But now there is even another constraint that you can impose here. For example, you may say something like that. Let's have a circuit which consists of only NAND, but let's them be 2 input, all of them. So the NANDs in the end happens to be all of the same kind, like this, 2 input NAND, okay? This means that, for example, in the past, that all the digital circuits can be designed using the same chip. For example, the 74LS00. That was the case in the past. So doing this final transformation, you can invent any networks of gates that, like the circuit 10, which consists of only NAND of 2 inputs, like this one here. And that is, the final variation. So let's summarize here. You have a truth table, which means the specifications for you. You have to go through the design process, and that is going to depend on the way you follow and the tools that you are using. You can go through a canonical representation of the circuit, or you can go minimizing by means of this Minitool exe or Logic Friday exe or another computer program, which is equivalent to the Carnot map. So that in the end you have a structural circuit or a structural architecture. So your combinational circuit becomes, an architecture which is structural. And this means that it's based on logic gates and equations, which is the same. Alright, that is what we call a structural circuit or a structural architecture. And this is going to be our first proposal for designing circuits, and this is going to be called the Plan A. Later on, we will see 2 more plans. The Plan B, which is going to be a kind of a behavioral implementation of circuits, and the Plan C2, which is like the Plan A, but about the idea of using a multiple file design. This time, we will refer to the Plan A, a circuit like this one, like the circuit 3, which is, it makes a small and is derived from a simple equation. So hi, let's just start now starting the process of designing architectures for a given truth table, okay? And that can be solved with any table. For example, let's consider the circuit C, the one that we found by means of an analysis of a given network. So the truth table was in the end something like this, you see, ones and zeros for the 16 different combinations. The function was, the C was a function of D1, D0, A and B. And this table was composed of some minterms, for example, the one that you see here, 0, 5, 6, 11, 13, 14, and 15. Those are the terms which are 1 in the truth table. Okay, so this is the specifications, the initial specifications of this design. And what we want now is to design circuits. But you know, this way, using the simplest, well, the most straightforward, if it's possible, because that is not always possible, especially when you have a lot of inputs, which are going to give you a lot of hundreds of even thousands of maxterms and minterms. But for this simple circuit, there is always the possibility of take directly the equations from the truth table, okay? Which equations? Well, the canonical ones. So let's invent the architectural circuit 1 and circuit 2. One of them is going to be based on maxterms and the other is going to be based on minterms. So in this way, from the very beginning, we can infer here two different circuits for this table. And there is nothing else to do. This time there is no even a plan here, because what I'm pretending to do is just translate the equation into a circuit. So perhaps it's something like this. This is what I have to do. For example, C is going to be the product of the maxterms, the terms which are not here. You see, the maxterm 1, the 2, the 3, the 4, the 7, the 8, the 9, the 10, and then there is the 12. Those are the maxterms. So if you expand the equation, it's going to be something like this: the maxterm 1 and the maxterm 2 and the maxterm 3 and so on, right? In a way that this list of maxterms can be expanded again in this way. The maxterm 1 is going to be, you know, a sum that is going to consist of all the terms. So D1 or D0 or A or B. Okay? The next, the 2 is going to be and the same thing, D1 or D0 or A or B. But now the number 1 is what you see here, 0, 0, 0, 1. So when you are writing maxterms, the terms that are 1 are the ones, the literals that are 1 are the ones that are not. So the maxterm 3 is something like this: D1, D0, A0 or B0. And the maxterm 2, right? And the maxterm 3 is just very similar: D1 or D0 or A0 or B0. And then the many more that goes behind. So you see, you have a long list of maxterms here. What is not a minterm is going to be a maxterm. And then what else? Well, this is an equation perfectly well written in Boole's algebra. So now what goes next is something that you already know. It is drawing the equation. You see, if you have an equation, that was the analysis principle that we had studied before. So if you have an equation, you immediately have a circuit. So which circuit? Well, let's organize it. It's going to be a buffer and next to it an inverter. Then there is another buffer and another inverter on the side. And in this way up to 4 times. So those are the literals to consider. The 4 terms, the 4 inputs of the system. Okay, D1, D0, A and B. So there is even here room for another one. So this is the case. This is going to be the D1, D0, A, and B. So what goes next? Well, you know that you have now D1, D1 naught, D0, D0 naught, A naught, and B naught. This is what you've got here, all the 8 literals. So you can go composing the maxterms simply taking the minterms this way. You see, this is the D1, then you connect the D0, and then you connect the literal A, and finally the literal B naught, which is that one here. In this way, you can connect OR, right? Not an AND, but an OR. So just draw the OR, and that is a wire that can be very well named maxterm 1. In the same way, you can invent the maxterm 2, but if you like, you can simplify the connections. You can represent a single wire, and now you can use crosses to indicate where the 4 wires are connected. For example, this is a connection, then there is the connection D0, and then you are choosing to connect A naught and the connection to B as well. So this is the same, the maxterm 2. And in this way you can go representing the next one, which is the maxterm 3, using you know, crosses or just dots as you like. So this is D1, this is D0, this is A naught, and B naught. So you can continue writing down the AND maxterm 12, which is going to be another term, D1 or D0 or A or B, but because the 12 is 1100, this is the term to consider. This is the maxterm 12, the last one, okay? So you can go generating the 1, 2, 3, 4, 5, 6, 7, 8, 9 ORs of 4 inputs to the last one. In this way you have the maxterm 12 as well, which can be represented in the same way using D naught, D1 naught, D0 naught, A and B. And so you have all the terms, and to finish the circuit, what is required now? Well, you can realize here that you have this is the OR that you are implementing here very well. So this is the OR, you know, the 4 input OR. So this is the AND that connects all the maxterms in this way. So if you translate that into a circuit, it's not that difficult to imagine that the circuit is going to be just like that. Another AND, I mean, that has 12 inputs, an input for every one of the maxterms. So in the end, what you've got is the C. And that's your first circuit, the circuit that you've been designing using the truth table represented as a product of maxterms. So now we have room to do the same using the equations based on minterms in the same way, okay? There is no problem in doing so. The equation is down there. So we can do the same thing. We can go and represent the C as the minterm 0 or the minterm 5 or the minterm 6 I see, or the minterm 11 or the minterm 13 or the minterm 14 and finally the minterm 15. This one is shorter for this application. And this is the sum of minterms. So very well, now you can represent every single term in this expanded way, but now as a minterm. And in order to do that, you have to consider again the, you know, the AND of every single input ordered correctly. D1, D0, AB, and here is the same, D1, D0, AB, and so on, until the last one, which is going to be D1, D0, A and B, the same way. But now, if you are considering a 0, and you are talking about minterms, you know, when you talk about minterms, the 0 is nothing but the 0, 0, 0, 0. And when you talk about minterms, the 0 goes not. So it's something like this. D1 not, D0 not, A not, B not, and the 5, you know, the 5 is 0, 1, 0, 1. So it's D not, D1 not, D0, A not, B. And the 15 is just like that. D1 and D0 and A and B. So you have again, you know, another equation pretty much like that, but now using maxterms. So this means that you can, at this time, write or draw the equation as a second. And to do that, you have to proceed in the same way. So for inputs, and this is basically for buffers and for nodes. Okay, so you have D1, D0, A and B as usual. So down there you have D1, D0, D1 not, D0, D0 not, A not, B not. So you have the first level of gauge, which are literals, and now you can proceed the same way. Let's implement this AND. You see what you've got here is an AND. So this is an AND. So you need now, what is required here is 1, 2, 3, 4, 5, 6, 7. 7 NAND of 4 inputs each to do so. So this is going to be the AND, okay? An AND, and then another one. So this one is going to be the gate to generate the minterm 0, and this one is going to generate the minterm 5, like this. Down there is going to be the minterm 15, all of them. So what about the minterm 0? Well, like this. You see, you have to use this connection D1 not, D0 not, A not, and B not. This is what is required to generate the minterm 0. And to generate the minterm 5, you can proceed in the same way. You can simplify if you like. Just a single wire and dots or crosses to represent what are you going to connect here. D1 not, D0. Okay, remember that those are minterms, so every minterm requires all the 4 variables to be synthesized correctly. So D1 not, D0, A not, okay, A not, so A not is that one here. No, this is A, this one, and finally B. That is correct. And the final one is D1, D0, A, and B. So in this way you have a line, you know, a second level of gauge, which is basically 4 input ANDs. So what is left to finish the circuit is simply consider the OR. So you are going to have an OR of 1, 2, 3, 4, 5, 6 inputs. So this is what is required now. A simple OR that sometimes we represent like this, especially when we have a large number of inputs. And this is going to be the C as well. So you have many inputs here, 6 of them. So this is the C. So this is another canonical circuit, the circuit 2, you know? So you can invent the circuit C, which is the one that has this table using the architecture based on maxterms, the canonical one, which is that kind of structure, or instead you can go and invent the second one, which is going to look like that way. And that is the development section. You already have the solution of the circuit, but you know that this is not all. What goes next here, you know very well, is a testing of these circuits. So why not, even if it is clear that it's going to be working rightly, but doesn't matter. Here you are at the beginning, so you must go practicing between the 4 different methods. So if this is your circuit, your objective now is to go and test. Okay? Test if the circuit is going to work or not. And you can do that in different ways. You can capture the circuit in Proteus, for example. This is going to be the method 1. You can copy the equation as it is, and that is not a very difficult equation to implement, and use it as an input to the engine Wolf and Alpha. So you have this equation and you have the table as well. So you can go back to the table to see if the equation is right. Or you can copy the equation in VHDL, and that is going to be the method 4. And do the same that we did using the EDA tools for solving circuits using VHDL. Okay? And finally, why not? Let's try some vectors now. You take another color, and for example, you can imagine now that you have these inputs. So D1, D0, A and B become something like, I don't know, 1, 0, 1, 0. So this is the 10, you see? You know now that the combination number 10 has to give you a result which is a maxterm. So let's see if this is true for the circuit 2 and if it is true for the circuit 1. Both are going to be the same circuit C. They are different, but they are the same circuit C. If you see it from this symbol point of view, from this entity view, right? So if you see it as a box, doesn't matter if internally the circuit is designed using minterms or it is designed using maxterms. Both circuits, indeed, whatever of them, the circuit 1, the 2, the 3, the 4, the 10, doesn't matter which circuit you are inventing. If you are applying now the combination 10, for example, you know that whatever circuit has to give you result 0. So let's check that, okay? This means that you are applying here a 1, a 0, a 1 and a 0. So a 1 in D1 is a 1 down here, and 1 not is a 0. Then you are applying a 0 connection at the input D0. You see, this is what you are doing now. 1, 0, 1, 0. Just a combination of the 16. So it is pretty right to do that at least 2 or 3 combinations in this way by hand, as if you were working through the method number 3, which is, you know, pen and paper, and solving some ideas here using pen and paper. So there's no need to go to the computers yet. You can do that by hand now. It's quite right, okay? So you imagine the situation. You are applying 1, 0, 1, 0 as the input of the circuit. So let's go and compute what happens here. So you have 1, 0, 1, 0. So 1 is 1, 0. 0 is a 0, and 0 not is a 1. This is what this device, this inverter are doing here. You have this doing here. You have a 0 and it is generating a 1. The same with the A. A happens to be 1 and A not is a 0. And the same with B. If B is, you know, stimulated with a 0, a logic 0, B not is just a 1. So this is the column of literals. Then what? What are you taking to the AND, for example, here is this, this is D1, so I mean that this is wrong, so D1 is 1, so this is a 0, this is what you are taking. So if this is 0, it happens that doesn't matter whatever else you've got here. you've got a 1 and something else, but doesn't matter. If this is 0, you already have a 0. 0 and anything else is a 0. This is a very simple way to test that. And then the M5, you see, if you have a 0 and you take it, like for generating the minterm 5, 0 is generating a 0. And finally, the minterm 15. Well, the minterm 15 is going to be 1, that's all right, but you have here taking D0, which is 0, so you are generating another 0. It looks like that the 3 of them are 0. So what about the others? Well, it is better to finish the circuit, so instead of 3, you have them all, the 7 of them. But you can do that using the equation, because the equation is the same of the circuit. So if the minterm 0 is generating a 0, the minterm 5 is a 0. Let's see the minterm 6, which happens to be D1, D0, A and B. But now you are driving this M6 with 1, 0. So you see, it's again another 0. Okay, what about the minterm 11? The minterm 11 is the same, D1, D0, A and B. Okay, but 11 means that this is 1, 0, 1, 1, so it's that way, okay? So now what is happening here? Because you are driving this with 1 and 0 not. So this is a 1. And then A is a 1 as well. But what about the B? The B is a 0. So 11 is generating for you another 0, the same as before with the others. So you can go with the 13. The 13 happens to be D1, D0, A and B. And the number 13 looks like to be 1101. So this is something like this, okay? So now what happens when you are applying this vector? This is 1 and 0. So very well. The 13, yeah, it is right. A naught is 0 and this is 1. So no, B is 0. So you have another 0 here. So what about the last one that we have to compute here, the 14? Well, the 14 looks like D1 and D0 and A and B, and the 14 is 1110, so the term to consider is that one. D1 and D0, A and D naught. So now you are inputting here 1 and 0 and 1 and 0 naught, which is a 1. But in the end, you've got a 0 as well for that term. So you see, C is 0. So that is what you are trying to test here. You see, you are trying to test that when you are inputting the number 10, you get a 0. So in this way, well, that's a good way to test it for some combinations. Naturally, this is why we have computers, to finish the job automatically by means of a computer or a simulation. But you know, time to time it's good to do that at least 1 or 2 times, using pens and papers and understanding what is the purpose of testing. You see, it's going to be all the time the same. Let's apply some vectors. And so there is always the question here, how many vector tests you have to apply to a circuit in order to test it completely. So for example, in this case, it is clear that you have to apply 16 vectors. So in the end, you can go and check if the circuit that you have captured in Proteus now in another sheet of paper and you have printed in and etc. Let's see if the circuit that you've been capturing is has generated this truth table. Alright, so in this way you can go and finish. Specify. Let it be like that. Solve the truth table for the circuit C. Plan. Let's use the canonical expressions. And here you are 2 possibilities, 2 different circuits, both valid. one of them based on maxterms and the other based on minterms. Develop. Develop is this kind of, you see, handmade operations of expanding the expression related to maxterms or the expression related to minterms, and the final development step is to go and translate the expression into a second. And fourth, test. Well, test means comparing your results with the ones from your colleagues or teammates. That's one way to do it. Another way, which is for you even more interesting, it's going to be, you know, practices in a little bit more in Proteus, so you can capture the circuit in Proteus and you can capture the circuit in Wolfram Alpha. So in this way you can go and solve the last step, which is testing if what you've been inventing here is right. Okay, here there is a point which is quite obvious that is going to work. If you have not missed any connection, it's going to work, that is sure. Because what you are inventing is the straight definition of the truth table. But that is not going to be that simple when we try to develop in the next recordings the circuit 3 or the circuit 4 or any other circuit based on NOR. You see, only NOR. So you will have a lot of work to do, simplify, etc., etc. So in the end, the testing step is going to be a fundamental one. Without the test, we cannot validate any kind of design. And we will start testing everything from the very beginning, as we did when we had to analyze a circuit. Remember, the analysis was in one way or another, but the step of testing was there because you simply had to compare the solution from 2 or 3 methods. And you can have to keep going, solving the problem until you have the same solution, even if you are using 2 or 3 different methods. So here is the same idea. You are inventing something, so please do not finish it unless you test it. Okay?